So when I came to Australia in 1995, we could look back in time because we had the new equipment, and I'll talk about that in a second. So the idea was to figure out if the universe was following the trajectory of the dotted line where there's not much stuff in it, or following the gray line where the universe has so much stuff in it that the universe stops expanding in the future, goes into reverse. So you can think about how you might do this if you can look back in time by looking at more and more distant objects. So for example, if the universe is going to eventually stop, the galaxies in the past, if I look at further and further objects, I will be able to measure the scale factor from the redshift, and I'm going to be able to measure their distances, and that will tell me essentially the trajectory of the universe back in time. And you get a slightly different distance and scale factor relation in the past if the universe is going to keep on expanding forever. Another way to think about it is looking through and measuring the universe's past expansion rate. Go through and you measure how fast the universe is expanding now. We call that the Hubble constant. And so if the universe, for example, is just coasting, it has almost nothing in it, then the expansion rate, the average expansion rate of the universe, isn't going to change over time. But there's a trajectory that defines where the universe has what we say has critical mass. It's that dividing line where when you throw the ball up, the ball goes on forever, or the ball comes back to Earth. And so that dividing line here tells you that if the universe was expanding faster in the past and it slows down quicker than this line, that is a line which defines where gravity wins and gravity loses, we can figure out the future of the universe as well as how much it weighs. So imagine when I look back in time, my galaxies lie exactly on that line. Then I know the universe is right on that edge where we're not sure what its ultimate future is. On the other hand, if the universe is slowing down slower, the galaxies lie in this part of the diagram, then we know that the universe is going to exist forever. So to measure the universe, we need to look back in time. But when we look back in time, we're looking far away, which means we're looking to things that are going to appear much, much fainter than they do nearby. So we need something bright. And the brightest thing that we know of in the nearby universe are type 1a supernovae. These are exploding stars. Now to understand them, let's look at the life of a star like our sun. Our sun, in about 5 billion years, is going to puff up as it finishes using all of its nuclear power and will collapse down to a tiny little star known as a white dwarf. White dwarf's about the size of the Earth, but the mass of the sun. But if our sun was instead formed in a binary star, that same process happens for the larger of the two stars. It collapses down, forms a white dwarf, and then the second star can go through that same process and make this white dwarf star become heavier and heavier. Now something amazing happens when it reaches 1.38 times the mass of the sun. It becomes unstable to gravitational collapse, but instead of forming a black hole, it explodes as a giant thermonuclear bomb. These are type 1a supernovae. And when we look at them, they're explosions that reach 5 billion times brighter than our sun, take about 20 days to reach that brightness, and they fade away into oblivion. These objects form more than 2/3 of the iron in the universe. They were figured out how to be used by a team in Chile, a team that I went and visited during my PhD thesis. And these people went out and used modern digital detectors to go out for the first time and figure out how bright these exploding stars were and to calibrate how many watts there were. When they were doing this work in 1990, and here we see Jose Maza from the University of Chile, they would go through and take a photograph, because we didn't have big digital cameras at the time, and they would put a photograph here and a photograph here. There's a little lever they could move back and forth, and they would use their brain, because we didn't have big computers either at the time, to find the new exploding stars. When I visited them in 1990, they really were kind of depressed. They were depressed because their first few exploding stars seemed to be very different from each other. And one of the hopes was, if you're going to figure out how bright these were, you're going to calibrate how many watts they were, you wanted to be almost all the same. So they showed me this figure, and they realized that this supernova, given the glorious name of 1990 AF, was fading more quickly and was fainter than the more normal objects that they typically found. Within a year or two, though, they had come up with the solution that this trend was always in all the objects they looked at, that the bright supernovae took a long time to reach their maximum brightness and fade away, where the faint one did that whole process more quickly. And we really understand this as how much iron they make today. And so when they were able to calibrate their data for the first time, this is when one of the young researchers, Mario Hamwi, came up to Harvard and showed us their data. This is what their data looked like. Every supernova here measures a measure of the scale factor, the redshift, and measures the distance. And you can see that you get this beautiful relationship where everything lies on the line of expansion. And that's because their method of measuring distances was really, really good. Now, it wasn't just their ideas that allowed us to do this experiment, it was also technology. And that technology came in the form of new modern digital detectors, which allowed us to scan for these exploding stars, which turn out to be very, very rare. Only every several hundred years in a galaxy like the Milky Way. So these new detectors, 2 megapixel detectors, so that doesn't sound that big now, but it was big back then, were coming online. And so we could take pictures with large telescopes to very, very faint levels of a big enough region of the sky to hopefully find one of these objects. The other piece of technology were bigger telescopes. In 1994, the Keck telescopes, the 10-meter telescopes, first started looking at the sky. And it was these telescopes that were big enough to allow us to gather the information we needed to, for example, measure the redshift to these exploding stars. So ideas and technology are what allowed this experiment to go forth.